Okay, welcome to lecture 8.4. Okay, let me finish this part on my media bias paper by just writing out the likelihood function. Now, the key is first, here's what I'm going to do. There are about 25,000 observations in the data set. So of those, about 10,000 involved legislators. Okay, there are data from the congressional record, speeches from the congressional record, and then about 15,000 were from media outlets. Okay, so what we're gonna do, just say T1 equals a number of congressional observations, and then T equals total observations. So T minus T1 equals number of media observation. Again, so T1's about 10,000. T is about 25,000. Now, to make it simple, wait. Here, let's. Okay, I'll get to that in a second. Let's define. So if so T equals an observation, and then if it's if a congressional observation, define I of T equals the legislator. So the number of the legislator. So we have something like 10 years worth of data. It's senators and members of the House. So let's see. So that is 535. I think it's something like 1,000 total legislators. So I of T is a number equals 1, legislator 2, all the way up to 1,000. Okay, so that's all it is you take whatever the observation number is. I just tells you what the number is of the legislator, and then so remember we have the ADA scores. Actually, it's the real ADA scores, or the adjusted ADA scores from my paper with Levitt and Snyder. For congressional observation, M of T, okay, if a media observation, M of T equals number of the media outlet. So there are 20 media outlets. We estimated C sub M for the slant, or it's like the ADA score for 20 different media outlets. And then what am I going to do? J of T equals the number of the think tank for observation T. So whatever think tank was cited by the legislator or the media outlet, define J of T as the number. So those are going to be numbered 1 to 200. Actually, it's going to be one. I'm going to get to that in a second. There are 200 media outlets, but it turns out most of them had very, very few sites. So what we did is we diminished that. We created a few into something called a mega think tank, and we had eventually 50 think tanks. That J of T is going to be number something 1 to 50. Okay, now, so by the way, and then J of T, this equals the dependent variable. Okay, so we for each of these observations, 25,000, we just look what was the number of the think tank that was cited, and we're going to call that. So that is J of T, and then what eventually I'm going to do is write the probability that, so if this, the first observation, if it's think tank number 32, what's the probability that the legislator, the media outlet cites number 32? Okay. And then we're going to multiply those all together. That's the product, and that's going to be the likelihood function. Okay, so here is the likelihood function, L. So we have all the A sub j's, and there's a different A for every think tank in our data set. So there's about 50 A's, except one we have to set to 0, so there's about 49 A's we have to estimate. B sub j, get 49 of those, and then C sub m, and that is there's 20 media outlets, there's 20 of those. All right, so okay, so our likelihood function is a function of those parameters, and it equals, now, to make things simple, we can always order our observations however we like. Now, what I'm going to do is I'm going to order them so all of the first observations, the first 10,000 or the first T1, are all the congressional observations. So we're going to take the product as T equals 1 to T1. So T1 is the number of congressional observations, and then the probability that the congressman cites think tank J of T equals E to the A J of T plus B J of T times X I of T. So remember, I is the number of the legislator, so X sub I is his or her ADA score. And then that is all divided by the sum, K equals 1 to 50. Okay, of E to the A sub K plus B sub K times X I of T, okay, times big pi, T equals T1 plus 1. Okay, so now we're starting the media data to cap T, total number of observations. And this is the probability now that the media outlet involved with observation T cites the J of T think tank. And so that's going to be A to the J of T plus B J of T times, now we don't have, XI is data, we don't have that for the media outlets. Instead we have, there's C, and which C do we estimate? Well, we look at the media outlet involved with the Tth observation. Okay, that's data, these M of T's and J of T's. Okay, and this is all going to be divided by K equals 1 to 50. E to the A sub K plus B sub K times C M of T. Okay, so that is the likelihood function. So, except remember that A sub heritage equals 0, B sub heritage equals 0. Otherwise, feed it into R, maximize likelihood function, it spits out the A's, B's, and the C's. Okay, now, let's see. What are, let's see, before I get to it, there's one more little identification problem we want to get to. But before I do that, let me first go back over why we had 200 think tanks in our sample. So we found this list of 200 think tanks. And at first, we were going to try to make it bigger. Then we thought, someone's going to accuse us of cherry picking our data. And we started off with these 200. We said, let's stick with that. Let's keep it at the 200. And that was from this website called something like How to Do or Where to Do Research, something like that. So we said, we didn't pick it. This website did. Here's the 200 think tanks. Now, it turns out something like 10 or 15 of those 200, no more than that. I think 10 or 15 had no longer existed once we did a research. And then another few had 0 sites at all to them. And so that's only 100, so that leaves about 175. And then of the remaining ones, a big chunk of them only had a few sites. So, once you get past the 50th most cited think tank, you're getting into think tanks that are only cited half a dozen times. So now given that, now remember this, a likelihood function, you have to compute the Hessian. Remember that? So some of these hill climbing routines compute the Hessian. Not only that, if you want the standard errors of your function, you've got to compute the Hessian. But for the standard hill climbing routines, it computes the Hessian at every iteration. Okay. Now, the Hessian, how big's the Hessian? Well, it depends on how many parameters you have. So if we had 200 A's, 200 B's, and 20 C's, so that's going to be 420 by 420. That's a pretty big matrix to try to invert. And when we started off, so we threw out 25 think tanks, and when we started trying with 150, we'd see that this was really, really going to take a long time just for the computer to churn through and give estimates. So as it was, when we get it down to 50 think tanks, the computer, I think it was a day, it might have been 2 days that it took. And we had various versions of our model, where we added in. The thing is, some of these citations involved a case where they were criticizing the think tank. So, well, we probably shouldn't count those, but maybe keep them in. We tried it both ways. There's one where the ACLU had just some kind of weird data, and the reason why is because Mitch McConnell learned that the ACLU came out against the McCain-Feingold campaign finance law. McConnell didn't like that law, and it turns out the ACLU came out against it, and he started saying, oh, look, here's someone from the other side of the aisle. The liberal ACLU even doesn't like this. So Mitch McConnell mentioned that fact about every time he could. And so what happened was something like a third or has a huge fraction of our data, of the ACLU citations, came from Mitch McConnell. We thought, okay, that's kind of weird. Maybe we should omit those observations. So we did it once while keeping them, once without, and we reported all these things in the appendix. So there was something like 15 or 20 different ways to run our basic model, and we did all the 15 or 20 extra ones in the appendix. But the problem is, remember, each one of those times you do it takes a day or two for the computer to run, okay? Now, that was with 50 think tanks. Now, what if we had kept all 200? Okay, so remember, basically what takes all the time is inverting that Hessian, okay? Now, if you double the number of think tanks, then that basically doubles the number of parameters, and then the Hessian is the number of parameters squared. So if you double the number of think tanks, that basically makes the Hessian 4 times as big. So if we'd gone from 50 think tanks to 100 think tanks, so that means it's going to take, instead of 1 to 2 days, 4 to 8 days. Right? And for each of those different kind of versions of the model, there's 20 of them. And if we did all, if we went up, doubled it again, 50 to 200, all of a sudden that's going to take 16 days for each of the versions of the model. So to save time, make it a little bit easier for it to estimate, what we did is we narrowed it down to 50 think tanks. And so what we did is said, well, let's pick the 45 biggest think tanks and then pick 5 mega think tanks. But then we tried to do it instead 43.7, 44.6, try these various different ways. And I reported in the paper, there was something like 7 or so different choices, natural choices, and we picked the median of those. Another reason we picked 50, because we started off doing this in Stata, and we got our seed values by running a multinomial logit. So I said this is similar to a multinomial logit. So if instead we had just used the congressional data, we could do a multinomial logit. That's what we did to get seed values. We said, let's only look at the congressional data. Let's use multinomial logit. That gives us estimates of the A sub j, B sub j. And then with those seed values, we do it for the entire data. Okay. One problem with Stata, though, in multinomial logit, it only allows you to have 50 total choices. And I told you I hate Stata. That's one reason. Okay, Stata would not allow. So when we're using Stata to get our seed values, we can't do more than 50 think tanks. And so that was another natural reason to pick 50. So for various reasons, we had a list of 200 think tanks. We narrowed it down to 50 total. More specific, I think I have this right. We did 43, the top 43 cited think tanks, plus we put all the other citations, collapsed them into one of 7 mega think tanks. And so what we did is we just looked at the average ADA score of those remaining think tanks, and then had cutoff values, so about 1/7 looked like the most liberal, the next 7th we'd call the next most liberal. So we ordered these, placed them into 7 categories according to most left wing to most right wing. Okay, that's how we formed those 7 mega think tanks. Okay, that is a lot of details you may not have cared about. They're all in the paper, though. Okay, so given that, so that's when we have that number 50. But I want you to know that the key is these things, when you're maximizing a likelihood function, the key is that Hessian. And the time it takes is related not to the number of parameters you're estimating, but the number of parameters squared. So you double the number of parameters, you make it take 4 times the amount of time. Okay, I want you to remember that's a key thing to learn from this class. Okay, now the final aspect I want to discuss is another possible identification problem. Okay, and this involves, what if we didn't have any congressional data? Okay, so we didn't have this part of the likelihood function. Instead, all we had is this part as our likelihood function. Is there an identification problem? And there is, and here's where it is. Notice before that x was an independent variable, now it's not. Now we've substituted c, a parameter that we're trying to estimate. Okay. And one problem is that we have this b, and it's similar to the Levitt paper. We have a parameter times another parameter. And if we had multiplied all the b's, every single b sub j, by lambda, and then we divide every single c by lambda, the same thing here, then the lambdas are going to cancel, and the likelihood function is going to be exactly the same as before. Okay, so what that means is that if we had no congressional data at all, now the same thing is not a problem here, and the reason is because this xi is data. It's not a parameter. So we can't just multiply all our data by lambda. Um, but if we multiplied the b times lambda, and we have some congressional data, this would change the likelihood function. So the key is to avoid that problem, this third potential identification problem. You absolutely have to have at least one congressional observation. Okay, and if you have only one, you're going to have like huge standard errors. But the key is you got to have a lot. And as it was, we had 10,000 observations. Turns out we used the entire congressional record that is posted online at the time, and it had gone back to, I think, like 2000. No, I think it had gone back to 1990. We even wrote the Library of Congress asking them to start including earlier years. They still haven't done that. But anyway, you actually have to have some congressional data, and then your estimates. It turns out to get your estimates to have tight standard errors, you need to have. It's good to have lots and lots of congressional data. Okay, so I think that's all. That is the likelihood function. In this class, we we really don't care about the substance. And but just in case you're interested, I think I have a handout. You have the paper. Here's the table. Here's our estimates. So here's the ADA score for the 20 different media outlets that we estimated. There's standard error right here. It comes from the Hessian. We had probably the key thing, this little figure shows how we can compare the slants of media outlets to the ADA scores of politicians. And a little anecdote, my research assistant at the time, my PhD, we hired something like 28 or so different undergrads to type in, to look up all this data. This was so arduous trying to get all this data. And at the time when I finished it, my PhD research assistant, Wesley Hussey, now a political science professor at Sacramento State, he's the one who created this figure. And you'll see, this is one of them, I think it's Microsoft PowerPoint. These things don't quite line up. I was such a stickler, saying, "Oh, you got to redo it. You got to get them lined up," and it never worked. And he actually got a little mad at me. How petty I was. It's close enough. I said, "No, this is the most important figure I will make of my career. It's got to be good. We got to have it lined up." And eventually he kind of saw it. Why maybe that should be the case. Okay, so that's the end of media bias lecture. What I want to do, though, I do have a homework problem. So I think this is 8.4, 8.5. I'll discuss a little bit what's going on with that homework problem. Okay, see you there.